The Hall effect. The Hall effect is an attempt to answer a rather fundamental question of electromagnetism. Can the free charge carriers of conductors experience a force due to a magnetic field when applied onto that conductor? So, what we already know is that a beam of electrons in vacuum can be deflected by a magnetic field. We want to address whether we can drift conduction electrons in a copper wire, for instance, so by deflecting them with a magnetic field. Well, in 1879, Edwin H. Hall, a famous scientist, rather a physicist, then a 24-year-old graduate student at the Johns Hopkins University, showed that we can. This Hall effect allows us to find out whether the charge carriers in a conductor are positively charged or negatively charged. Beyond that, we can measure the number of such carriers per unit volume of the conductor. This is called determination of the number density of charge carriers. So let us dive into Hall effect, as it is well understood in terms of electromagnetism as studied in high school physics, and also we need a little algebra, and other than that I think we can grasp the fundamentals of Hall effect. So let us take this screen as vacuum, and we apply this magnetic field, which we denote by a cross encircled here in red. So that means the direction of magnetic field is normal to the plane of screen, and it is going into the plane of screen. I denote that by B, and it is a vector field because I can attach a magnitude to it and a particular direction, and it obeys the triangle laws of vector addition. So it is a vector field, and so that encircled cross means the magnetic field is perpendicular to the screen and into the plane of the screen you are observing right now. Now if this is an electron carrying some charge E minus, so what happens when we keep an electron in vacuum and we apply such a magnetic field? Well, interestingly, nothing happens as such. It is still the same happy electron as it was the day before we switched on the magnetic field. Jokes apart, it is actually due to the fact that static charges do not interact with magnetic fields at all, because static charges do not create any magnetic field. So they are not able to interact with the magnetic field. For being able to interact with the magnetic field, which is into the plane of the screen in this case, those charges need to actually move with some velocity. Let us take that as V. And this electron, let us say that this electron is kept in vacuum and it is moving with some uniform velocity V. V is a vector, and so if it moves, now imagine for a second that the magnetic field is switched off. We have a switch, we can switch it off. So what will happen? The electron will move along this dotted path. It will move in a straight line with uniform velocity V with no force acting on it. But when we switch on the magnetic field, we have to now apply Fleming's left hand rule to determine the direction of magnetic force on this electron exerted due to the magnetic field B. That will be perhaps downwards in this case, because our index finger will represent the magnetic field into the plane of page. The direction of current is opposite to the direction of motion of electron. So accordingly we get the magnetic force F as we represent it. It is a vector force, and that force is acting downwards at right angles with the velocity, at right angles with the field. We have taken this to make it simple. This is the basics of electrodynamics, you can say, and so we are analyzing what will happen to this path along which the electron is moving. Well, it will not move in a straight line path. The electron gets deflected and moves along the yellow path I have indicated, and that is the new trajectory. It is experiencing a magnetic force because it itself is creating a magnetic field to interact with the red marked field. So thus this electron will get deflected when the magnetic field is switched on and move along the yellow path as indicated in the figure. Now observe that a static charge creates an electric field also. So the electron is not only experiencing magnetic force. Well, if some other charge was present, that would experience an electric force due to the electric field of this electron. Well, if it moved, then that would also experience some magnetic force due to the magnetic field I have applied, and the total force on that electron would be called the Lorentz force. So Lorentz force on a charged particle is basically the sum total of the electric and magnetic forces acting on it due to the electromagnetic field acting in that particular region. In this case, we have taken it as vacuum. Now let us talk about Hall effect, rather the concept of crossed fields, as we discussed a few minutes back. So we are drawing a magnetic field which is into the plane of the screen and which is perpendicular to the plane of the screen. It is a region of uniform magnetic field, and the magnitude of that field is constant, which is so it is uniform. And in that region of uniform magnetic field, we have kept a copper conductor of some particular width, d, let us say that width. And now in this copper wire, you are aware that there are some charge carriers. A particular interesting aspect of Hall effect is that it allows us to determine what are the charge carriers present inside a conductor carrying some current. So in this case, we already know it is electrons which are moving, because they are the charge carriers. They are free to move. They are the main carriers of the negative charge, but the direction of conventional current is opposite to the direction of motion of these free electrons. Now we denote the magnetic field with B. It is a vector field, so we assign a vector sign as per the conventions we have learned in vectors. Now the direction of current is indicated by this blue arrow. Let us denote it with I. Current is flowing in that direction, which means electric field is also in the same direction as that of current from top to bottom, which is why the current is in that direction. So we can say that the electrons are moving upwards with some drift velocity Vd, and they have a charge E minus. This is from our basics of high school physics we have studied previously. Well, what happens when this moving charge, which is an electron over here, interacts with a magnetic field B? Well, it experiences a force determined by Fleming's left hand rule and gets deflected to the right side of this conductor along the path I have drawn. This was previously discussed, and this is what exactly was demonstrated by Edwin Hall when he was just a graduate student at some university, So this Hall effect has many experimental applications, many consequences which have some theoretical importance, and something of utmost importance is that we make silicon conductors and sensors based on this Hall effect, and many other effects can also be explained with Hall effect, and many errors, precautions can be avoided or taken accordingly if we know the basics of Hall effect. So what happens is that due to the drift of electrons, the right side of the conductor gets accumulated with negative charge. As you can see, electrons are getting accumulated on the right side of this conductor, right edge of this conductor, and they leave the uncompensated positive charges, the fixed ions rather, which were initially on the left side. They are not moving, they are fixed. They get accumulated on this left edge of the of the conductor, and so that has a consequence. The separation between the left and right side of this conductor creates an electric field. Now let us redraw the field, because now I need to demonstrate something else. This was the conductor. This is the negative charge accumulation on the left side. Positive charge gets accumulated on the right side. And what we observe is that some electric field denoted by that green arrow is established from the left to the right. So this is the direction of electric field denoted by E, and we have our magnetic field V. The drift speed Vd is acting on the electron in the direction as was shown in the previous diagram, and we can say confidently that this electric field will exert a force on the electron in a direction opposite to the direction of the electric field. Now that force is in this direction, that is Fe. Let us denote the magnetic force as Fb. So what happens? Though some of the electrons continue to move like this in spite of this unbalanced situation of forces, but we might say that after certain mathematical instant of time, there comes a situation when Fb, the magnetic force on the electron, is equal to the electric force due to the electric field. What happens then? The electron will not move in any of the edges of the conductor, rather it moves along the straight line with Vd as its uniform speed, and the current still flows like this. So what is the consequence of this? It means that there was a particular potential difference set up due to this electric field. Let us mark this edge width as d. Now we know something, that if we have electric field in a region, this electric field is rather uniform, so we can say some potential difference V is set up between the two edges of the conductor, and that is equal to the electric field into this width of the conductor. We know this from basic of electrostatics. We also know that the current is equal to N, E, A and Vd, where N is the number density of free electrons, number density. Well, I'll explain that thing a bit later. E is the charge on an electron, A is the area of cross section of that conductor, Vd is the drift speed of the electrons. Well, so what are we doing with all these equations? Are we playing around with them? Literally, playing with equations of physics has huge consequences. We can get wonderful results. It can give some practical results, but that is not the reason why we do it. We do it for a different reason, for pleasure. So let me write down the equations. So we got the potential as this. Now let me tell you something. This potential, as a matter of fact, it is called the Hall potential difference. This V is the Hall potential difference. It's just a term in honor of Edwin Hall. And we also know that when the electric force is equal to the magnetic force, then this equation is applicable. We can cut these small charges and we get the electric field to be equal to drift velocity times the magnetic field, an important result to be used in our theoretical derivations. What are we trying to arrive at? Are we beating around the bush, or are we trying to arrive at a particular result? We know something important. We know that the Hall potential difference is electric field times the depth, the width strip, and this electric field can be written like this. And we also know that the number density of free electrons is denoted by N. It means the number of free electrons, or rather charge carriers, per unit volume of the conductor. This is the meaning of number density of electrons. So we can write that N as I by the drift speed times the charge on the electron times the area of the electron the area, cross sectional area of that conducting strip we have taken in that magnetic field. So what are we arriving at? We can replace this V with electric field by the magnetic field, and we can replace the electric field itself by this expression. So we are arriving at this particular result. So that becomes E times, right, and this E is replaced as V by D. So what do we get? So from this step we are getting N as equal to IB by V E A D. This is the final expression of today's discussion. Now here I can make one last substitution as follows. Let me write it out neatly. That means here I have taken this L to reduce the form of the final number density expression. L simply means the area of cross section of the conductor divided by the depth. This is L. L is called the thickness of that particular strip. So from Hall effect we can get the number density of free electrons of a particular dimension. So we can do that. Also we can do something else. I said sometime before that it has some experimental importance, which means when I was doing Hall effect, you might have observed that this side was positive and this side became negative. There was some electric field, there was some magnetic field like this, and the electron was not moving either this way or this way. It was just simply moving like this with some Vd. So what I want to say is that the experimental importance of Hall effect is that across this depth D, if you attach a voltmeter like this, you attach a voltmeter V, let us say, you can get a reading of the Hall potential difference across this width. And also using the voltmeter reading, we can actually predict whether this edge or this edge is at a higher or lower potential. In this case, this edge is at a higher potential, this edge is at a lower potential, this is higher potential, this is lower potential. But suppose you want to contradict my statement by saying that no, this is not. Let us assume that the charge carrier is not an electron. If current is flowing in this direction, let us assume that the charge carriers are positively charged. They are moving along the direction of current, which implies that if the force starts acting on this charge carrier, it moves to the right. It moves to the right edge by Fleming's left hand rule. So what happens is that this side becomes positively charged, but this very last statement I made, that the this right edge becomes positively charged, this is contradicting your voltmeter reading. It will say no, this is this left edge is positively charged. So which means here in case of a copper conductor, it is obviously impossible to say that the charge carriers are positively charged. What I mean to say is that it is experimentally verified that the charge carriers have a negative charge on them, and they are simply electrons which are free to move, belonging to the last orbit. And thus we come to an end of Hall effect. Thank you.